Hello everyone! The shader we are going to create in this video definitely isn't one of the most useful effects for game development. It's more of a detour from more complex algorithms and includes several interesting techniques that might come in handy. So let's take a look at how to program a four-dimensional cube. This time, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background. So I'll create a new scene and set everything up for this kind of shader. Right-clicking the scenes folder, create a new scene. It is a user interface type, and let's call it tesseract. Yeah, it's correct. Now I'm right-clicking the root node and adding a child node of the type colorAct. Let's change the color in the inspector to black, and I'll expand layout transform and change the size to the full HD 1920 by 1080. Okay, and scrolling down to the materials section where I create a new shader material. In the material property, click it and add a new shader type, shader mode canvas item, and the path will be shaders /tesseract.gg shader create, and clicking again to open it in the shader editor. And as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function, deleting vertex and deleting commented out light, Ctrl S to save. Okay, here we go. I'll start by adding a resolution parameter, which will need to recalculate the aspect ratio, since we want all the edges of the cube to appear the same length. So let's put it here, uniform vec2 resolution equals vec2 1920 and 1080, our full HD resolution. Okay, I'll also go ahead and write the usual beginning of the fragment function. To make the object appear in the center, we'll shift the coordinates origin and adjust the aspect ratio. Vec2 uv equals uv minus 0.5, and uv.x is multiplied by resolution x divided by resolution y. Okay, now I'll add a function where we define the coordinates of all 16 vertices of the hypercube. This can be a bit harder to visualize, since four-dimensional objects aren't exactly intuitive. Anyway, for simplicity, it's enough to know that the number of vertices doubles with each dimension. A one-dimensional line segment has 2 endpoints, a two-dimensional square has 4 vertices, a three-dimensional cube has 8 vertices, and a tesseract therefore has 16. And since we are in 4D, they will be represented by vec4 objects with components of either 1 or -1. It will look like this. So vec4 array of 16 elements, and let's call it get tesseract. Okay, no parameters are necessary, and vec4 verts 16, so let's define the array and we will return it in the end. Alright, and now I need to fill it with values 4 int I from 0 to 16 I++, so this is the cycle where we do all the calculations. Vert I index is vec4, and I think I'll put it to separate lines. Okay, I'll first write it, then explain. A and 1 is not equal to 0 times 2 minus 1 minus, I said. Okay, this is the first line. And now I'll duplicate it 3 times and do this change. 2, 4, 8, and yes, that's it. So what am I doing? This is a logical AND, meaning that we take only the first bit of this number, and if it is not 0, we will multiply we'll always multiply by 2 and subtract 1, but if it's not 0, this result will be 1, as the true value will be converted to float. So the result is 1, and in this case, if it is false, the result will be -1. Okay, so this is basically the generator of the tesseract vertices, and let's add it to the fragment function, scrolling down and adding this line. Vec 4 vert 16 is simply the result of our getTesseract function. Okay, now, since 4 dimensions can't be easily displayed, we need to perform a projection, first into 3D and then onto a 2D screen. We'll want a perspective projection so the object appears more spatial, so I'll add 2 uniform parameters to define perspective along the W and X and Z axis. Uniform float. Perspective W with a hint range, and I think the initial value was 2.5 and the range from 1 to let's say 5 and the step point 0, 1. Okay, and the second one, uniform float perspective Z, another hint range, and this time the value is 3.5, and again it goes from 1 to 5 with the step point 0, 1. Okay, you might be wondering what the W axis is. If I switch to 3D editor, we can see the X, Y, and Z axis that define 3D space. The W-axis adds a 4th dimension, and since it's not easy to imagine, we'll just trust that it's there. And why W? As you know, UV is used for pixel coordinates, and the next letter in the alphabet is W. Okay, so I'll write a function that performs the projection from 4D to 3D. And let's put it here. I'll just expand this window because there is still nothing to display. And let's put it after the getTesseract function. Vec3 project 4D. And the parameter will be vec4 v for a vertex. Okay, notice that we take a 4-dimensional point and return a 3-dimensional one because this is the projection. So float delta v dv is perspective W minus v point W. This is the 4-dimensional vector, so the coordinates components are x, y, z, and w. Okay, and now float f for the perspective calculation is 1 divided by max dw and 0.0001. This is just a fail-safe, no, 0. Just this fail-safe, because in case this difference is 0, we want to avoid dividing by 0, and let's return vector 3 v dot x, y, z times f. So this is a well-known formula for the perspective projection, and next comes a very similar function for projecting from 3D to 2D. I think I can just copy and paste and do some changes. So this time we return vector 2. The name is project 3D and the input parameter is only vector 3. And let's call it the Z perspective Z, and we are using again a z component. This is the same except this is dz, not dw, and we return vector 2 and composed only from x, y components of the vertex v. Okay, and finally, let's add a function that combines both of these projections. So, vec2 project of the four-dimensional vertex vec4v and return project 3D of project 4D of v. Okay, we can now add the projection to our code. We'll want to control the scale of the display, so I'll first introduce a new parameter called scale, going up to the uniform parameter section and uniform float scale with a hint range and initial scale let's set to 1, and it can go from 0.1 to, for instance, 2 with a step point 0.1, and now the code in the fragment function that converts the four-dimensional vertices in this array to their two-dimensional projections. So let's call it vec2 PTS, 4 points, again 16, size 16 of this array, and now for I from 0 I to 16 I plus plus, and let's do the projection. So PTSI equals project of vertex I and multiplied by our scale parameter. What exactly is not correct here? Of course, it's supposed to be integer. All right, this is correct. Cool. So far, we don't see anything. If I show it, we can see there's really nothing. We don't see anything, partly because we are not rendering anything yet. There is nothing like the output variable color. And also because the vertices themselves aren't visible. We need to connect them with lines to form edges. So I'll continue by adding a function to compute a segment defined by 2 points. It's a formula I've already used in one of the previous tutorials, and it looks like this. So let's add it here, and I'll call it float segdist, distance of segment, and vec2b for the point, vec2a for the first boundary, and vec2b for the second one. And the formula looks like this. vec2, let's call it AB, is simply the difference B minus A. Now, float D is clamp of dot product of B minus A and AB. Okay, divided by another dot product, dot. What did I write? Dost. Okay, dot. Let's get back to the second one, AB and AB. All right. And we're clapping to the range from 0 to 1. Okay, and let's return the length of the vector P minus bracket A plus T times AB. Okay. Furthermore, we'll want to modify the color shade based on the depth of the current edge. So I'll add a function that performs this calculation using the average value of the W component of both vertices. So float edge depth with the parameters vec4 vertex 1 and vec4 v2 for the second vertex, and let's return the arithmetic mean. So it is simply v1.w plus v2.w divided by 2. Okay, So now we compute all 16 edges in the fragment function. For the current pixel, we determine the distance to the nearest edge and its depth. We store both of these values in new variables. Okay, and this is the last, a bit more complicated segment of code. After that, we'll definitely get to displaying something. So I'm back in the fragment function, and let's add it. Float min d starts at 1e9, which is 1 billion. So we are going to find the closest edge to the current pixel, and we'll do it by comparing everything to this value and decreasing it. And as for the shade float, let's call it best W, because the shade is based on the W on the fourth dimension of the edge. It is for color mixing. And now we need to create the loop. So for int A from 0 to 16, A++, and the second edge for comparison, so from int b starts from a plus 1. It's definitely necessary to do it from 0, b less than 16, b plus plus. Okay, and now the calculation. So int diff for difference is a XOR b. I'll get to that. Or anyway, this is an exclusive OR operation, meaning that exactly one bit set means that these vertices share the edge. Okay, and now let's detect that. So bool is edge is simply diff is 1 or diff is 2 or diff is 4 or diff is 8. Okay, and if this is not true, so we are not detected edge, let's simply continue in the cycle, skip the rest. And if it is, we'll do this. Float d for distance is segdist, our function, with uv coordinates, pts-a and pts-b, our two vertices. Okay, and now if d is less than min d, we are just finding the least distance, min d equals d, and best w equals our edge depth function applied on the vertices, because we will be using the fourth dimension, the w. Verts b. Okay, and yes, that's it. That's the whole double loop. And let's render it finally. The value best w is in the range from -1 to 1, so we need to remap it to 0 to 1 to use it for setting the final color. So float edge depth is best w times 0.5 plus 0.5. Next, we'll need a line thickness, so I'll define a new parameter for that, scrolling up and adding the parameter uniform float line thickness with a hint range, and the initial thickness, let's set to 0.01. Okay, and it goes from 0.01 to, let's say, 0.2 with step 0.01. Okay, scrolling back to the end of the fragment function, and since the value is quite high, let's divide it by 10. Float thickness is line thickness times 0.1. Okay, now we'll use a trick to smooth the resulting line using the smooth step function. Float, let's call it line AA for anti-aliasing, smooth step of thickness, then the second edge is thickness times 0.3 for instance, and the value is minimum D. All right, we need to add colors now. We'll have two, one for the inner edges and the one for outer edges. Let's add both as uniform parameters. So uniform vec4 RGBA colors, color inner, with a hint source color for the color picker in the inspector, and the initial value vec4, and I think I set 0.2, 0.8, and 1, and alpha 1 again. Okay, and the second one, uniform vector vec4 color outer, again with the source color hint and initial value vec4, and this time it was 0.8, 0.3, and 1, and 1. Okay, and scrolling back to the end of the fragment function, and let's use the edge depth variable, this one, to determine the final color and mix these two. So vec4 edge color equals mix of color inner, color outer, and edge depth as the weight factor. Yeah, edge depth. Okay, fine. To allow setting any background, we'll add a parameter for the background color. So again, scrolling up to the uniform parameter section and adding one more color. Uniform vec4 color background. Again, a source color, and let's start with a black color. Vec4 0, 0, 0, and 1 to make it opaque. 1. Okay, scrolling down, and let's perform the final mix of the output. So color, the output is mix of color background, edge color, and the value is our line AA, anti-aliasing. Okay, and let's take a look. Very well, we finally got something. It looks a bit strange if you check these lines. Some of them are not quite visible because some of the edges need to be improved with a soft glow to stand out. So I'll add one more parameter called glow radius. Okay, scrolling up to the uniform parameters section one more time, and let's add it here, uniform float glow radius with a hint range and the initial value 0.01. We need just a very soft glow, and range from 0.01 to 1 with the step 0.01. Okay, and we'll use it in the code with the exp function using a negative parameter. This is what we did several times in the previous tutorials. So it will give us a diminishing glow at the distance from the as the distance from the edge increases. So there is the definition of line A here. Let's add it after that. Float glow equals, as I said, exp of negative max min d minus thickness and 0, so we cancel out the possible negative values, divided by glow radius times 10. Yeah, I think no. All right, and let's combine it with our edge. So I'll define one more variable called float combined, and it will be simply the linear interpolation or something very similar to that clamp of line AA plus glow times 1 minus line AA. All right, and the clamping range is 0 and 1, of course. Okay, and I'll define the glow color as a semi-transparent version of edge color and blend the two colors together, which will fix the poorly visible edges like this or this one. So where is the edge color? Right here, and after that I'll define vec4 glow color equals edge color times this vec4 1 1 1, so white, and 0.5 to decrease the alpha value, and vec4, let's call it final edge, equals simply a mix of glow color, edge color, and again line AA for the weight factor. Okay, and let's fix the color, the final color output. So it's a mix of color background, but this time it's final edge, and the value is combined. Okay, wait for it, and now we have a much better result. It still doesn't look too cool, but that's because the hypercube needs to rotate for the fourth dimension to really stand out. So next comes the implementation of this functionality, and to control it properly, we'll add uniform parameters for rotation speed across all 6 planes. So I'm scrolling up again to the uniform parameter section, which is quite long right now, but just 6 more parameters, nothing else. Uniform float, speed xy with a hint range, and let's set the speed to 0.3, for example, and we want to rotate in both directions, so from -2 to 2 with the step 0.01. Okay, and now to save some time, let's copy and paste 5 times. 1, 2, 3, 4, 5, and rename the values to xz, xw, yz, yw, and zw. So all 6 combinations of these 4 axes, and I think I set some other values, 0.5, 0.2, so the rotation is more interesting, 0.5, 0.4, and 0.6. And now we have to go to the inspector, shader parameters, and reset these values. Okay, this is correct. And now for the rotation function. While in 3D we rotate around the x, y, and z axis, in 4 dimensions we rotate around planes formed by these combinations of x, y, z, and w axis. So that this gives us 6 functions, and the first one looks like this. Let's add it right after the uniform parameters. Vec4, let's call it rot for rotation, xy, and vector 4, v for the vertex, and float a for the angle. Okay, and now the typical rotation functions. Float c is cosine a, and s equals sine a. This is a short way of writing both float c and s variables. This is just to save some space, because we'll be then copying and pasting 5 times like the uniform parameters. Okay, and we return vec4, and now c times v dot x minus s times v dot y, because we are rotating around the xy plane, so we're using the xy components, and s times v dot x plus c times v dot y, and then v dot z and v dot w. These two didn't change. Okay, so this is the first one, and as I said, I'll now create 5 copies on this function. I think we again expand this window, and I know this part is prone to typos. So if your version of the shader doesn't work, you can always use the one I include in the Godot shader pack. So copying these lines, and now 1, 2, 3, 4, 5, and again I'll rename to xz, xw, yz, yes, yw, and ZW. Okay, and of course we need to fix these formulas. So for the road xz, it will be c times v dot x minus s times v dot z. Now here, this time the second one is not changed, so v dot y. Now the third one is s times v dot x plus c times v dot z, and the fourth v dot w. Okay, now the third one, xw. So this is the same, cx minus v dot w, and v dot y, v dot z, and this one w, and let's delete the rest. Is that correct? I hope so. Now the yz, so we start with v dot x and rotate with v dot y minus v dot z, v dot y. Shit, sorry about that. Here it is back. So w and z, and the final one is simply v dot w. Okay, now the function rot yw, so it starts again with v dot x. Now for v dot y we have it here, minus v dot w. Then the third one is v dot z, and y and w. Okay, and the final one rot z dot zw, I mean. So it's v dot x, v dot y, and c times v dot z minus s times v dot w, s times v dot z plus s times v dot w, and wait a minute, I think something I did wrong, or no, it seems to be correct. Perfect. Okay, so then I'll insert a function that applies rotation to all 16 vertices. Yeah, right here. After these rotations, let's write void rotate tesseract with parameter in-out vec4 16 verts. As we know from previous tutorials, the prefix in-out means that this parameter is input parameter, but it will also work as an output one. So it will change the parameter which is used in the fragment function to call this function. Okay, and let's write the rotation function for int I from 0 to 16 I plus plus. Ooh. And now vec4 v is verts of the index I, and the rotations. So, no, V equals rot xy and V, and the parameter is time times speed xy. Okay, and let's again copy and paste 5 times, 3, 4, 5, and rename to xz, xw, yz, yw, and zw. And of course the speed parameters must be changed accordingly. xz, xw, yz, yw, and zw. Okay, and of course, what's wrong? Speed rot xz. Speed xz is probably not defined correctly. Oh, I have xx here. xz, okay, perfect. And of course, we need to assign the result to the output array as well, equals v. Cool, so this is it, and all that's left is to start a rotation, which we can easily do in the fragment function. So let's show the tesseract again, scroll down to the fragment function, and let's find it right here, get tesseract, and after that I will call rotate tesseract with our vertices. Yeah, as the parameter, wait for it. And here we go. We are done. And as usual, we can play around with the parameters. So let's find them in the inspector. And here, for instance, I change the perspective W. We can see how it zooms in and out, or the similar thing can be done with the camera on the Z-axis. As for the scale, it is actually something like a combination of both. We can increase the line thickness, so it looks thicker. We can change colors. I think I won't do it right here. What I can do now is to change the glow radius. Now it's definitely glowing a lot more, but I think I like this version a bit more. And as for speeds, let's zero them out, all of them first. So we can observe now it goes only across these two planes. And so, for instance, what happens if we rotate only around the xy plane? Do you think we already expected? Yeah, something like that. Or this, and it looks much more like a cube right now. So I think we can achieve some very interesting effects with a combination of these values. Let's just reset them. Okay, by the way, if we wanted to switch the camera from perspective to orthographic, we can easily do that in the projection functions by removing the multiplication by the variable f. So let's find it. Here it is, project 4D. And let's start with the 4D first. So I'm deleting the f and wait for it. Okay, let's change the scale so we can see more of that. Yeah, that doesn't look bad. And what if we do the same in 3D? So the project 3D function and deleting the F. And I think I need to change the scale again. Yeah, now the projection is definitely orthographic, and we can get maybe a bit better 4D look and feel, or maybe not. I think it might be still better with the perspective camera, and let's reset the scale to the original value. Okay, and that's everything. Thank you very much for watching. After all, it wasn't as short a video as I originally hoped, but hopefully it was at least somewhat useful. At least we've shown how to perform anti-aliasing of straight lines and how to enhance it with a simple glow effect. Next time, we'll definitely return to dimensions that are more practical for games. For now, take care, good luck with your projects, and I'll see you in the next video.